Alright guys, this is the second video in solving rational equations. Today it's going to be all the different types of word problems that go with these rational equations. You're going to see three different types of word problems with these. One will be a distance type, one will be a mixture type, and then one will be a work type of problem. We're going to go through each one of each type, and then you guys are going to do one of each type. And like your quiz and test will be like these three types. It won't be anything really far-fetched out besides these three types of distance, mixture, and work. So to start off, we're jumping right in. The first problem is this. Sandra is rowing a canoe on Stanhope Lake. Her rate in still water is 6 miles per hour. It takes Sandra 3 hours to travel 10 miles round trip. Assuming that Sandra rowed at a constant rate of speed, determine the rate of the current. Okay, so we know that the formula to use here is D equals R times T, distance equals rate times time. The only thing we're going to, which, you know, we've done that before. The difference between this one and any other ones is we know how long it took her the entire trip. Okay, we know the distance for each part of that trip. What we really need to work on is finding that rate. So since we know the time, the total time amongst the two, we're going to take this same equation and we're going to solve it for t. So I'm going to divide both sides by r and get t equals d over r. Okay, and to do this, you basically set your equation up in three separate parts. Now, when you're on a river, obviously, I mean, it says, you know, lake, but it should be a river, you know, because that way there's a flow to it. But anyways, you have two different motions. When you're going down, you're going with your time spent going down river, that's with the current. And then when you come back, it's your time against the current. And then that's equal to your total time. Whoops. Oh, that'll be alright. Okay, so we know the total time is 3 hours. And the reason why we did this is because we have a separate rate for whenever she's going with the current and when she's going without. So that's why you can't just like set this up as a single ratio or proportion or whatever, because you have a separate rate for when she's going with the current as opposed to when she's going against. We know that these two rates added together gives us the 3 hours she spent on the round trip. Okay, so for both of these right here, we're going to have some sort of d over r scenario. Okay, and for the distance part, we know it was a 10 miles round trip, so we know each trip down and back was 5 miles. Okay. And we know that Sandra's rate was 6 miles per hour. Now we're looking for the river's rate. Okay, we're looking for the rate of the current. And so for that reason, you have to make sure and be careful that you set these up properly, because whenever you talk about the second one, the time against, you don't want to do the rate of the river minus her rate. You want to do her rate minus the river's rate. Okay, so you have to make sure you set that one up correctly. The 6, so the 6 mile per hour that she's rowing, plus the rate of the current, which is helping her. And then the other one is 6 miles an hour that she's rowing, minus the rate of the river, which is going against her. We add those two up, and it's equal to 3. So that's kind of the setup to these problems. So you kind of look at it as the total amount of time that she spent rowing, her distance over her rate with the current, her distance over her rate against the current. Okay, so if you need to write that down, go ahead and pause here because I'm going to shrink it down so I have room to actually solve this. Okay, there it all goes. So we have the equation being 5 over 6 plus r plus 5 over 6 minus r equals 3. We get the LCD of this guy, which is going to be 6 plus r, 6 minus r. and then we multiply by what's not there. So 5 times 6 minus r plus 5 times 6 plus r equals 3. Now notice how neither 3 doesn't have a denominator, so you need to multiply it by both 6 plus r and 6 minus r. And if you would multiply those two together, which is what I do to save a little space, it'll give you 36 minus r squared. Okay, from there you just solve it like a normal equation, so you distribute everything you got, so 30 minus 5r plus 30 plus 5r equals 108 minus 3r squared. Get your like terms on the left side, so 30 plus 30 gives you 60. The 5r's cancel out, so equals 108 minus 3r squared. You're going to subtract the 108, which gives you a negative 48 equals negative 3r squared. Divide by negative 3, and I switched the way my equation is, so r squared equals 16. Square root of r, or square root of 16 is plus or minus 4. Since we want the positive rate, her rate, or the rate of the river, is 4 miles per hour. Okay, so it's all about this setup that's hidden right over here. Okay, so you want to make sure you get that setup good. As soon as that's done, it's just solving a rational equation afterwards. So the hard part today is definitely going to be the setup. Okay, as you guys can see, there's a question on the way. Be careful with this one. You may have to set up your rate differently because this one you're looking for the plane speed, not the wind speed. So pay attention to that when you work this one out. And also, when you get to the end, I'll give you guys this fair warning. Hopefully I remember to mention it in class the other day that you'll definitely need your quadratic formula for this one. This is for one of them. This is the one you need your quadratic formula on. So when you get down to it, you'll get a quadratic equation. Just go ahead, plug it in your calculator, and simplify it that way. And then you want the positive answer for there. So go ahead and answer this one. The speed of the wind is 20 miles per hour. If it takes a plane 7 hours to fly, 2,368 miles round trip, determine the plane's speed in still air. Okay, so hopefully, like I said, you got the right answer here. It's 339.5 miles per hour because you're looking for the plane. So yeah, it's going to be a little larger than Sandra rowing down the river. So you got to pay attention to the context of your problem here. You're looking for a plane speed, not somebody paddling. So it's going to be just a little bit faster. Like I said, occasionally a quadratic will show up in here, so that quadratic program is a good thing to hold on to because you don't have to. I don't think this even factors nice since you end up with decimals. Or actually, take that back. This doesn't factor since you end up with ugly decimals like that. So having that quadratic formula program is a really handy piece of program to have in your calculator at all times. So if you ever delete it or you ever have to reset it, make sure you get it from somebody or myself. So that's the distance problems. We're moving on here to the mixture problems type of problem. So here we kind of go with this setup. Mia adds a 70% acid solution to 12 milliliters of a solution that is 15% acid. How much of the 70% acid solution should be added to create a solution that is 60% acid? So the setup for this one, we are going to eventually get it as a ratio. But the ratio we want to set up is kind of like this. We want the percent of your final amount over, the 100% that it's going to be out of, which equals the amount of acid over the total amount of solution. Okay, because remember, that solution is not going to be full acid. It says that final solution we want it to be 60% acid, which means it's going to be 40% other stuff. All right, so the way you set this up, and I like this table setup. I think it helps you pay attention to what you're doing. You label it you have a two row table. The first row you're going to label amount of acid. And then the bottom row, you label total solution. Okay. Now, one of them is going to be like the solution that's already there, right? It's the solution that we're starting with. And the solution that we're starting with is the 12 milliliters of a solution that's 15%. Okay, it makes sense because Mia is adding the 70% solution. So we're starting with 12 milliliters of a solution that's 15%. And to figure out, well, first off, if it says 12 milliliters here, that means there's 12 milliliters in that solution. So 12 goes here. And to figure out the amount of acid that's in that solution, you're going to take the amount of it times the strength of it. But you got to make that a decimal. So you want to take the amount of solution, which is 12, times the strength of it as a decimal, which is 0.15. So that's your first kind of column of your table. The second one, I kind of set up this way and show it to be the one that you're adding to it. So we're adding a 70% solution. But if you scan through the problem, nowhere does it say how much of that 70% solution we're adding, because that's actually the question. How much of the 70% acid solution should be added? So we don't know how much of this is added, so there's your variable. So we know it's 0.7 for the strength, but we don't know the amount, so x goes there. Same way down here below, x is there. Okay. And then this last column, so this is our original column, this is our adding to column, and to make your new solution, which is what's going to go here, you're going to add those two things together. So 12 times the 0.15 plus the 0.7x to get your strength over the amount of solution that you're going to have, which is 12 plus x. So this is the one side. This is this part. Okay, it's the amount of acid in our new solution over the total solution. To figure out, so we're going to take that. Watch me what I do here. So we're going to take that, and we're going to set it equal to the percent that we want it to be over the strength of it. Okay, now you can set that up two ways. You can either do it as 60 over 100. You could also do it as what I'm going to eventually do, 3/5 and reduce it. Okay, so I'm going to go ahead, I'm not going to, just to save me some space, I'm going to go ahead and erase 60 over 100 and make it be 3/5. And then from there you cross multiply them. So whenever you cross multiply that, make sure you do your distribute work. I also clean this top part up, so 12 times 0.15 will give me a 0.18 when I get there. So cross multiplying, so 5 times a 1.8 plus a 0.7x equals 3 times 12 plus x there. Okay, so then you go ahead and distribute. So 5 times a 1.8 gives you 9. 5 times 0.7 gives you 3.5x equals 36 plus 3x. And then from there it's just your normal linear equation. So 27 equals 0.5x. Divide both sides by 0.5x equals 54 milliliters. So you would need 54 milliliters of the 70% acid solution to get the balance to work out correctly. Okay, which is going to lead into the next mixture problem for you guys. Jimmy adds a 65% fruit juice solution to 15 milliliters of a drink that is 10% fruit juice. How much of the 65% fruit juice solution must be added to create a fruit punch that is 35% fruit juice? So show me the setup to this one, and then I'll give the correct answer on the question. Okay, so there's the setup table for this one. 15% or 15 milliliters of 10% over 15, 0.65 times x over x sets that up. 35% total, so 35 over 100. Keep this as 35 over 100 because you have to scale this up, so don't try to make this like 0.35 over 1. It doesn't work out the same. And then you cross multiply. I reduced this too, so that's why you see the 7 and the 20 here. I reduced that by 5. So then 7 times this, 20 times all that, distribute through, like terms, divide, you get 12.5 milliliters. So the last type of problem then turns into the work problem, and they always seem like they're the most confusing, but they're really kind of simple once you get it. So the first one here, every year, junior and senior class at Hillcrest High School build a house for the community. If it takes the senior class 24 days to complete a house and 18 days if they work with a junior class, how long would it take the junior class to complete a house if they worked alone? So the way we're going to set this up is kind of like a distance rate time problem, except it's going to be just a little bit different. So what we're going to do, we're going to have the seniors, we're going to have the juniors, and then we're going to have them combined or together. So if it takes 24 days for the seniors to build a house, there we go. If it takes the seniors 24 days to complete a house, then each day they're building 1/24 of that house. Okay, so if it takes them 24 days to build a house, each day they build 1/24 of the house. So that's their kind of rate. All right, they build a house at 1/24 per day. All right, and it tells us in there combined with the juniors, we know that they completed in 18 days, so their combined rate would be 1/18 of a house per day. And the juniors we don't know, so we label it, like 1 over x or 1 over j. Added together equals. So you have 1/24 plus 1 over x equals 1 over 18th. Since you have a variable happening in one spot, you can subtract the 1/24 over, which gives you 1 over x equals 1 over 72. Then you cross multiply, so x equals 72. So it would take the junior class 72 days to complete the house all alone. And that's basically how you set up the work problems for all of them. It's going to be some sort of like that. It takes, how long it'll take them over the day unit equals their rate. So that's kind of the setup for all of these. I'm not going to try to trick you on work problems. If I try to get you somewhere, it'll either be on the mixture or the distance problems. So work problems are pretty straightforward. Last one you have is this one here. It took Anthony and Travis 6 hours to rake the leaves together last year. The previous year it took Travis 10 hours to do it alone. How long will it take Anthony if he rakes them by himself this year? So go ahead and work this one out the same way, and go ahead and give me an answer. Okay, so hopefully you worked it out to get 15 hours. Notice that this one, the time parameter just kind of goes wherever the problem takes it. For example, the last one was days, and you kept it in the context of days. This problem, you're talking in hours, so the context is in hours. So your time parameter just goes wherever the problem dictates. It's not going to change, of where you have to convert or anything like that. So that's the lesson, guys. The final assignment for this chapter is page 576, 577, 9 through 11, and then 22 through 24.